Okay, so in the last video, what I talked about was developing a Bradford assay. Standard curve in which your standard curve was absorbance at 595 versus amount of protein measured in micrograms, really any type of milligram, nanogram, whatever it could be, but in micrograms was the option that I chose, so that would be amount of protein. Now I'm going to say specifically amount of bovine serum albumin. In this video, I'm going to talk about the alternative approach to developing a Bradford assay standard curve, in which your weight or your axes for your graph are absorbance at 595 nanometers, and it would be your concentration. And I'm going to put, sorry, BSA, your concentration of BSA, concentration of BSA. Okay, and that would be measured in, let's say, micrograms per microliter. So the math that you use is a little bit different. In both cases, you can ultimately figure out the concentration of an unknown, which is really why you would do a Bradford assay to begin with. Some people prefer the method this first method that I've discussed, and some people prefer the method that I'm going to discuss in this video. One thing that makes it quite simple is in this method that I'm going to be describing here, if you are getting the concentration for the protein sample in question. So there's not any additional calculation like what you saw at the end of my previous video. So I want you to be familiar with both of them, some of the kind of benefits and some of the conveniences that each present you. So I'm going to go ahead and forge ahead with that. All right. So in the previous presentation, basically what we did was we plotted this, our absorbance at 595 as our y-axis, and this column as our x-axis. For what we're going to be doing now, essentially what we will be doing is we will be plotting the same y-axis, but it will be against this x-axis. What will make things a little bit different for you is I'm going to scribble these out because these values are not going to be particularly useful for you. And really, this whole column is not going to be something that you need to worry about. And whenever I'm going through this and doing some of the math, you might think, well, this is pretty similar to the previous method, and you're right. It is fairly similar, but there are some significant differences in the process that you're going to go through in order to do this. For the sake of simplicity, I'm going to only going to do about 5 or 6 calculations. One thing that I'm scribbling out right here on the left-hand side of the screen, or that I just scribbled out, was working stock, because the source is going to be fairly important. And essentially, what you're going to do is you will make a series of dilutions. And this is not a 1 to 10 or 1 to 10 dilution into a 1 to 10 dilution into a 1 to 10 dilution. You have a little bit of flexibility on what you want to work. So what I'm going to do is I'm going to say you will start out with, let's say, 100 microliters of your WS, your working stock. Okay, 100 microliters there. What you're going to do is you're going to take 20 microliters of it, and you are going to use it here. Okay, so your total volume, I'm just going to write TV here, will be 920 microliters. And for every single sample that you do across the board will be 920 microliters. And you know what some people will do is they'll change this Bradford reagent volume. They'll change it to 1,000 microliters, or 1,000 microliters. But the volume of the protein sample and the volume of the Bradford reagent are going to be fixed. So for every single trial, you will take 20 microliters from a protein sample, you will take 900 microliters from a Bradford reagent. The reason that I said some people will do 1,000 microliters is that's simply preference. There are some people who opt to have it be, or they'll have they'll have 1,000 microliters of the Bradford reagent. For our demonstration, it doesn't really matter what you use. Another column, that I'm going to go ahead and scribble out because it's effectively one that we don't need to worry about because we're not going to be plotting it, is this one right here. So you can kind of see some advantages. I'll write advantages. Less to plot. And fixed volumes, which if you watch the previous video, sometimes you're getting 20 microliters from the working stock, 50 microliters from the working stock. It gets a little bit hairy. Okay, so at any rate, also for the sake of simplicity, I'm just going to go ahead and omit, because I'm not going to put together numbers for my y-axis, because what I want you to do is understand the process of this and not get lost into the graphing of it. Essentially, the graphing is the exact same, but you just have to remember your axes and what you're solving for this. Okay, so we have a working stock, and imagine that is the sample, or that's the test tube that your IA provides you with. Say it has 100 microliters of a 20 microliter stock, or 100 microliters of a working stock that has a concentration of 10 micrograms per microliter. Okay, what we would do is we would write the concentration of our protein sample, 10 micrograms per microliter. Okay, now what we're going to do is we'll take 20 microliters of this, and that will be used for this data point right here, or generating that data point. So we're left with 80 microliters. So I'm just going to write this as gone. Okay. Of the 80 microliters that remain, we're going to take 20 more of them. And those are going to go into what I'm going to call T1, or tube number 1. So I'll just write here T1. Okay. That test tube number 1, what it's going to have is 80 microliters of DH2O. So tube 1 now has a total volume, a TV, of 100 microliters. Now my concentration, my BSA concentration here, it's not a molar concentration, but my BSA concentration here is going to be, well, I took 20 microliters from this 10 microgram per microliter stock, and I diluted it to, or added 80 microliters to get me to a total volume of 100 microliters. So this is going to be a stock that is 2 micrograms per microliter. Okay, so I'll write here 2 micrograms per microliter. All right, now with T1, so I'm going to try, for T1, this test tube number 1, or my first dilution in this process, 20 went to right here, and then I'll take 20 more and I'll make T2. I feel so inclined to make a reference to Terminator 2, Judgment Day, but I'm not going to, aside from the reference by saying Terminator 2, Judgment Day. It's just a great movie. To that, I'm going to add 80 microliters of DH2O. Okay, so now in this T2 judgment tube, I've got a total volume of 100 microliters. Now, what's my concentration here? My concentration, I took 20 microliters from T1, and I added to that 80 microliters of DH2O. So my BSA concentration here is going to be and I like to just think about it in terms of fractions. It's going to be 1/5 of my concentration of T1. And what that means is this will be approximately 0.4 micrograms per microliter. Okay, so now my next one is going to be 0.4 microliter, 20, and so this I'll label as T2. Okay, so all that I'm doing is just repeating the same process for making all of these different tubes. I made T1, T2, T3, and now I'm going to be making T3, which I will take 20 microliters from T2, or actually what I need to, my system here, I've got T2, and from that I take 20 microliters. I go to add 80 microliters of DH2O, making T3, Rise of the Machines, that's the Terminator 3, but my test tube number 3 here, it's got 100 microliters as the total volume. My BSA concentration, well, it is 1/5 of my T2 fraction, or my T2 sample. And so that would mean that this is 1/5 of that, what would that be? 0.08? Yeah, that sounds right. Yeah, 0.08 micrograms per microliter. So T3 is 20, 0.08 micrograms microliter, and you would just continue on making T4, T5, T6, T7, and so on. Okay, as you can see, our concentrations are getting smaller and smaller and smaller. So 0.08, well, a fifth of that would be 0.5, 0.198, I don't know, 0.1, let's see, I'm going to pause it so then I can do the math. 0.016 micrograms per microliter. Okay, and 20 microliters. Okay, so obviously my concentrations are getting considerably smaller and smaller and smaller, and they will continue to do so. Now, things that you can do, so this is just a perfectly fine way to set things up. You're making these dilutions, and the only thing that so one of the things that I like about the previous method is you do not have such a dramatic drop in concentration and drop in amount, because whenever I'm looking at a plot, so bear with me here on my drawing, A595 versus BSA. What I want to see are data points that are fairly close together, and obviously I want them linear, but I feel more comfortable with data points that are packed together like this. So then whenever I get an unknown, and I'm going to use a different color for my unknown, and I plot it, my absorbance is right there, I have a data point very near it that I can feel comfortable with, and I can say, oh, well, I knew this sample had this much protein, and I have this unknown that's super close. And so I like this display of data rather than something like, that, because these data points, I'm like, ooh, if I could fill in these gaps, it might give me a little bit more confidence that my data is more accurate. Now, with that said, though, one of the things that you can do if you set this, or if you decide to use this method, is you don't have to. So what I would do, I would keep this as 20 microliters, but when you're starting with 100 microliters and you use 20 microliters for your actual assay, you could arguably use and be confident that you'll be able to continue to do so. You could use, 70 microliters from that work or from that original stock to make T1, in which case you'd maybe make an adjustment and say, okay, I'm going to use 70 microliters from my stock, and then I'm going to add 30 microliters of water. Okay, so for each time, now T1, I'm going to take 20 microliters for my trial, but then I'm going to take 70 microliters of it for my next dilution. So this right here is a point, the amount that you're taking to make that series of dilutions, that's going to influence kind of how closely packed these data points are, how many data points that you can acquire, what they look like, how far they go. And so what I would maybe recommend is I would do with this 100 microliters, I would use 20 microliters for the trial, and then I would take, say, 50 microliters. And I know that I just drew 70, but I would recommend, and I'm going to rewrite this, I would do, 50 microliters, and then add 50 microliters of water for T1, and then in T1 I take 20 microliters out, I take 50 microliters from that T1 and add it to 50 microliters of DH2O, and from that I take 50 microliters and so on. And I just like to land at something like 50 microliters because then I'm looking at 1/2, and so I'm looking at 1/2 of the concentration from the preceding sample. So I see these steps that are a little bit closer together, and it just kind of makes me, I don't know, it makes me sleep well at night. All right, well, I hope this is helpful, and I hope that these two different techniques are something that you can kind of find a preference and maybe find one that you work with a little bit better. It makes a little bit more sense to you. Questions, though, that I want you to be able to answer is, if I gave you a sample, I'm going to erase my plot down here, and it seems kind of a trivial question. It seems almost like a Gen Chem 1 sort of question. But a question that I always like to be able to answer, or for my students to be able to answer, is if I gave you a microcentrifuge tube that had let's say 100 microliters of a protein sample that had a concentration of 36 micrograms per microliter. Okay, the significance of these numbers is really kind of irrelevant. I want you to be able to answer the question of how much protein do I have? And this is something that, like I said, it's almost just a Gen Chem 1 question. And if you wanted to treat it as such, you could set this up as a dimensional analysis problem, because you have a two-dimensional number, 36 micrograms per microliter, a concentration, and you have a one-dimensional number of a volume. You could set this up as 100 microliters. That's on the top, that's in the numerator. Well, we need to get microliters in the denominator. Well, the good thing about that is we can just write out 36 micrograms per 1 microliter, and we know that if we have 1 microliter of it, we have 36 micrograms, but lo and behold, we have 100 microliters of it, therefore we have 3,600 micrograms of protein. Similarly, if I said that I have, 125 micrograms of protein in 12.8 microliters, I'd want you to be able to do that simple calculation. That's genuinely just, or that's just getting it down to a concentration in micrograms per microliter. I know this seems like a lot, but here's the benefit of these video lectures. You can watch this and you can rewatch it. And I hope this isn't the case, but in the event that you rewatch it and you find an error or something like that, um, please ask me about it. But I'm pretty confident in all these calculations right here. Um, both of these techniques, or both of these graphing techniques, give you a little bit of flexibility, but more than anything else, what they do is they show you a relationship between light absorbed at 595 nanometers and amount of protein in a sample. I hope this is helpful, and I hope that I didn't have too many parting messages there, but thank you very much, and have a good one.